Hello everyone, in this video I will speak about QMM additional question which we get from the last videos. The question was, show in detail how the classical equation of motion in Jacobi-Hamiltonian formulation can be converted into Newton equation when we move to the Lagrangian frame. First of all, this is the Jacobi-Hamiltonian formulation. Here we have Sk, which is the phase of the nuclear wave function, and here we take the partial derivative of this Sk with respect to the time, which is equal to the sum of all the nuclei we have, 1 over 2mi, the mass of the nuclei, and then we have the partial derivative of Sk with respect to the Ri squared plus Ek. Ek is the sum of all the electronic potential we have. So it's look like we will have some here, but it's not shown here. It depends on the notation we take. We need this equation to convert it to Newton equation, which is this. Here we have the mass multiplied by the acceleration, which is equal to the force, and we can say that this force comes from the derivative of the potential with the minus sign. This is the classical Newton definition of the force. But why we want to use the Lagrangian mechanics, not the Newtonian one? In the Lagrangian mechanics, we describe the motion by the energies, and because the energies is scalar, so we will not work with the vector and with the direction, which is much easier in some way. While in the Newtonian mechanics we describe the motion by the force and we use vector to describe that. We can say like one important point to use the Lagrangian mechanics because it's more extensible to the other physical theories than the Newtonian mechanics. Let's start from the first equation we have, and if we move to the Lagrangian frame, so we will describe our system as individual particle, and every particle have a momentum. This momentum can be defined as the partial derivative of Sk with respect to the Ri. If we just substitute this momentum into our first equation, we will have this term and the sum of all the 1 over 2 the mass with p square is the kinetic energy. In some reference they note the kinetic energy as Ek, but because we have here Ek, we will just note that this total kinetic energy will be T, and we will change also this Ek to be V, the potential energy. And then if we just add the Lagrangian definition, which is L equals to the kinetic energy minus the potential energy. So our equation will be the partial derivative of Sk over with respect to the time will be minus L. And then if we just move this minus L from the right side to the left side, so we will have L plus partial Sk over dt equals to 0. And then we will change the Lagrangian with another new Lagrangian equivalent to the first one, which is L prime. L prime equal to L plus delta Sk over delta T, so we will have L prime equals to 0. It's not always possible to do this thing, but we will use one properties of the Lagrangian, which called the non-uniquenesses. So if we have a first Lagrangian L. We can multiply this Lagrangian by any constant not equal to 0 for sure, and we can just shift or add any other constant like p on it, and we will have L prime which have the same equation of motion that the L can provide us. So we can say that this transformation is correct if only we have this function, which is f, have two fixed end points, and these 2 points should be equivalent to each other. Why we say that? Because here we add constant, and if we make integral over this constant, it will not change anything to the equation. We can test these properties like this. We said that both Lagrangian L and L prime provide the same equation of motion, since the corresponding action S and S prime are related by the equation. If we write S prime Q equal to the integral over the L prime dt, and we will substitute what is L prime from this equation, we will have the integral from the first time to the final time L, which is SQ, plus the integral from the first time to the last time df qt dt. We can remove this dt with this dt, and the integral of df will give us f in the final point minus f in the first point, which we see here. So if we have 2 points equivalent to each other, the first one is equivalent to the last one, we can safely remove this term with this term, and we will have S prime Q equal to S prime. And let's test if our equation can do that. We have Sk in our equation, and this Sk, because it's the phase of the nuclear wave function, so it starts from 0 and end at pi, which is 2 fixed points, and we know the exponential of 0 and the exponential of 2 pi is the same. So we can safely say that L prime and L can give us the same equation of motion. So let's start from L. As we define L is T minus V, which is the kinetic energy and the potential energy, we will apply the Euler Lagrangian equation. Here we have the partial derivative with respect to Q, and here we have the partial derivative with respect of the time and the partial derivative with respect of Q dot. In this case, we should write Qi because it depends on the nuclei or the particle we have, and we have Qi also, Qi dot. So this equation is the same as this equation, but we should add just I, but for simplicity we will just use the first one. We will not add this I. So we will add the Lagrangian on the left hand side and on the right hand side. On the left hand side, so we will have to take the derivative of the kinetic energy with respect to Q and the derivative of the potential energy with respect to Q. So let's deal with the first term. We have the derivative of the kinetic energy with respect to Q. We can add this dq inside the sum, and as we define the momentum as the velocity times the mass, here we have the mass and here we have the velocity q dot. We have squared here, so we will just write mi squared here, so we'll have mi squared over 2mi, and we have the derivative of the velocity with respect to the coordinates, which equal to 0. Why we say that? Because the momentum depends only on time. It's like if I take the momentum on x coordinate and I just want to take the derivative over x, which is equal to 0, because the velocity on x-axis with respect to the coordinate is always 0. So we can say that dq dot over dq is equal to 0. And the second term here, we have the derivative of the potential energy with respect to q. Here we have d over dqv, which is equal to nabla. We know the nabla is the derivative operator, and we can write in the first notation v as equal to ek, which is the same. So the left hand side at the end will be equal to minus nabla ek. And if we look at the right hand side, which is here, we will apply the derivative of the time and the derivative of the velocity to the kinetic energy and to the potential energy. We will start from the kinetic energy here. We will add d over dq dot inside the sum as we do before, and we will write the pi as the mass times the velocity, and here we will have dq dot squared over dq dot, which is 2q dot. It's like when we take x squared and we want to take the derivative of x. So the derivative of x squared is 2x, and we write it here. So at the end we will have the sum over the mass times the velocity. And if we want to take the derivative of the time after that, we will have that the derivative of the time, we will just put it inside the sum, and we will have the sigma over I miq dot, which is the acceleration. If we look at the second term, here we have the potential energy, and we take the derivative of the potential energy to the velocity, which equal to 0, because the potential energy just depends on the coordinates or on the distance only, didn't depend on the velocity. So the right hand side will be at the end is the sum of miq dot. And then if we add just the left hand side and the right hand side, we will have minus nabla ek equal to the sigma over I miq dot. And because the ek is the sum over all the electronic potential energy, so we can remove the sum from the both side, from this side, and the sum which is embedded inside the ek, and we will have the Newtonian equation of motion minus nabla ek equal to miq dot, which is mi, the second partial of rik with respect to the time squared, which is the Newton equation of motion. And that's what we want from this video. Thank you so much for attending this video. If you want to learn more about simulation and the force field and what we use in theoretical chemistry, please visit the YouTube channel and you can learn more. Thank you so much.